everyone. Today we're going to be talking about half-life. We've talked about it a little bit in class, but when we're talking about half-life, we're talking about the time it's required for half of the nuclei of a radioisotope sample to decay to products. So remember that radioisotopes are the only isotopes that will decay. Our stable isotopes are already stable, so they're not going to undergo decay. So this is how long it takes for half of the nucleus of a radioisotope to decay. And we can take a look at this table that has a couple of varying half-lives so that we can see. I put carbon-14 here because that's one of the most common decays that we might talk about, especially when we're talking about carbon-14 dating, so figuring out how old fossils are. The half-life of carbon-14 is 5.73 times 10 to the third years. And the type of radiation that would be emitted in carbon-14's decay is beta. Remember, B, the beta sign, and minus, that's beta decay. Hydrogen-7, on the other hand, has a very short half-life. So it has a half-life of 2.1 times 10 to the negative 20 seconds. That means that every 2.1 times 10 to the negative 20 seconds, half of hydrogen-7 is decaying. Half, and half, and half, and half, as opposed to a series of years, right, for carbon-14. So that's an extremely short half-life. This one will also emit beta radiation and gamma as well. And then tellurium-128, this is an even longer half-life than carbon-14, 2.2 times 10 to the 24th years. So it will take that long for half of tellurium-128 to decay, which means it remains around for a really long time. When it decays, it will undergo beta radiation, or beta decay as well. So let's take a look at this graph over here. I'm going to switch places a little bit. We have a graph here of carbon-14 decay. So what I've done here is we have, on the y-axis, we have the percent remaining. And it should always go up to 100% because that's what we're starting with, is 100%. Okay? It should always go down at the very lowest to 0%. I do want you drawing this graph in your notes, so please make sure that you do have this. We have 100 to 0%, and along the x-axis, we have years, all right? So the first one that I have is 5,730 years, 11,460 years. If you take a look, each of these numbers in years is increasing by 5,730 years. So each one is going up by 5,730. So if I'm going to graph, or if I'm going to actually just interpret this graph of carbon-14 decay, I see that at time 0, I have 100% of my sample left. Great. I can see at time 5,730 years, I have about 50% left. At 11,460 years, about 22.5% left. And each time, each of these is decreasing by half the percent, right? So each of these little dots, you can see it decreasing by half the percent. You can also see that this starts out really rapidly decaying. And then as we get down here, it gets exponentially smaller, all right? So this is an exponential decay curve, or an exponential decay graph, right? So that's what I've written here. It's exponentially getting smaller. Now, if we wanted to find the half-life on a graph, here's how we're going to do it. We're going to draw a horizontal line at 50% until we hit our line that we've drawn here. So at 50%, I'm going to draw a line until I hit my line. I'm going to draw a horizontal line until I hit the curve, okay? Then I'm going to draw a vertical line down from there to the x-axis, right? So straight down, this is going to be a straight line. You'd be wanting to use a ruler for that, but I just don't have a ruler that will work right now. So draw a vertical line down to the x-axis. The number that it hits at that x-axis is the half-life. So we can see where it's hitting. It's 5,730. This is the half-life of carbon-14, 5,730 years. You will have the opportunity to interpret graphs in that same way when we practice this a little. So let's take a look at, if we don't have a graph, how are we going to solve these problems? We can use the table method, Okay, so I'm going to show you a generic table and I'm going to show you a specific table. Nitrogen-13 emits a positron and decays to carbon-13 with a half-life of 10 minutes. All right, so every 10 minutes, half of that nitrogen-13 would remain. Right, so it's going to decay to carbon-13. Assuming a starting mass of 2.00 grams of nitrogen-13, how long is 3 half-lives? All right, so we can take a look here. We always want to start at 0 half-lives, all right? We always want to start at 0, otherwise your table is going to get not extremely messed up, but you'll be off by 1 half-life. So at 0 half-lives, how much of my sample is remaining? 100%. At 1 half-life, how much is remaining? Well, what's 50% of 100? 50%. At 2 half-lives, now we have half of 50% left. We have 22.5%. At 3 half-lives, we have half of 22.5% left, which is, oh gosh, math, which is 12.75? Oh, 11.25. Wonderful. That should have been easy. 11.25%. And at 4 half-lives, we have, I did not do that math right. Oh my gosh, that's why I didn't do it right. That's why I was saying 12. 50%, half is 25%, right? Half of that, 12.5%. Half of that, 6.25%. Okay? So we want to know how long 3 half-lives is. So here's what we're looking at. 3 half-lives, we know we have 12.5% left. Here we're going to want to use our specific table. All right? Now, the one thing that I want to point out here is that after 0 half-lives, we know that we have 100% remaining. That's why we're always starting with 0. 0 half-lives or 0 time. After 1 half-life, obviously we have 50% remaining. So for our problem here, let's see, we have a half-life of 10 minutes. So at 0 minutes, I have my full mass. At 10 minutes, which is the first half-life, I'm going to have half of this left, which is 1.00 grams. At another half-life, we're 10 more minutes into it. So after 20 minutes, we're going to have 0.500 grams left. At 30 minutes, which is 3 half-lives, right? 1, 2, 3 half-lives. How much do we have left? We have 0.250 grams. Now, I didn't really need to write minutes here because I have minutes here in my table. That's why I didn't write my grams all the way down here, because I have grams as my unit in the table. So, after 3 half-lives, I have 0.250 grams remaining. How long is my 3 half-lives? 30 minutes. All right, so in answer to the question, 3 half-lives is 30 minutes. Okay. Now, just take notice that in my table, I am looking at sig figs. All right, I'm starting with 3 sig figs. So, although I'm not going to round till the very end, if I were looking for the mass, I would want to make sure that that final mass has 3 sig figs. All right, we're going to take a look at 2 more problems. I should actually get on the other side. So example 1, how many half-lives have passed if 255 grams of cobalt-60 remain from a sample of 8,160 grams, okay? So we're going to use this table. The very first thing you need to do is figure out what are the variables that you're putting in your table. We just saw number of half-lives, time, percent remaining, and mass. You can use any really combination of those, all right? So how many half-lives? Well, that tells me that number of half-lives is going to be one of them. How many half-lives have passed if we start with 8,160 grams and we end with 255? I'm going to say mass should probably be my other unit. All right, so what half-life are we starting with? Or how many half-lives? Always 0. Always 0. All right, so my beginning mass right here, that's my starting mass, is 8,160 grams. okay? After one half-life, how much do I have? I'm going to get my calculator just so I can do this faster. Okay, we have 4,080 grams. After two half-lives, we have 2,040 grams. All I'm doing is dividing each one of these by 2. After three half-lives, we have 1,020 grams. I'm going until I hit 255. After four half-lives, I have 510 grams. After five half-lives, I have 255 grams. All that's happening here is each time my mass is decreasing by half, okay? So, how many half-lives have passed? If 255 grams remain, 5 half-lives have passed. 5 half-lives. That would be my answer. All right? Now, my last problem here. A sample of 3.00 times 10 to the 7 radon atoms are trapped in a sealed basement. The half-life of radon is 3.83 days, okay? About how many radon atoms remain after 31 days? So, back over here to my table, I need to figure out what I'm going to put for my units. Well, I see the half-life of radon is 3.83 days. That's a time. So I'm going to put time here. Typically, in this first column, you either want time or number of half-lives. In the second column, you're either going to have percent remaining or mass or number of atoms. I see here that we're working with number of atoms. So I'm going to put number of radon atoms here. Okay? Now, what time am I starting with? Always 0. So after 0 days, how much of my sample remains? Well, exactly what I start with. 3.0 times 10 to the 7th. That's how many radon atoms remain. After not after one half-life, after 3.83 days. That's one half-life. I'm going to have 1.50 times 10 to the 7th atoms remaining. Okay? After another half-life, and I've done this just so it's going to be easier, after another half-life, that's 7.66 days. How much remains? Half of this. Now, if I divide 1.50 divided by 2, I get 0.75. I want to make sure this is in correct scientific notation. So, this is 7.50 times 10 to the 6th. All right? I'm putting this in correct scientific notation, so my coefficient is between 1 and 10, not less than 1. All right? The next half-life, the third half-life, 11.49 days have passed. Right? And I can actually just go all the way down until I hit about 31 days. So, another 3.83 days passes, and I'm at 15.32 days. I don't have to keep writing days. Another half-life passes, and I'm at 19.15 days. Another half-life passes, I'm at 22.98 days. Another half-life passes, I'm at 26.81 days. Another half-life passes, 3.83 more days, and I'm at 30.64. That's pretty close to 31, so I'm going to stick with that, all right? So, half of 7.50 times 10 to the 6th, I get 3.75 times 10 to the 6th. Half of that, I'm at 1.875 times 10 to the 6th. Notice I'm not rounding for sig figs until the very end. Another half-life passes, and I get 9.375 times 10 to the, I've now gone from 6 to 5, right? Because this seems to be incorrect scientific notation. Another half-life, and we are at 4.6875 times 10 to the 5th. One more, and we're at 2.34375 times 10 to the 5th. And the last one, we're going to round this for sig figs, so we can only have 3 sig figs. I get 1.17 times 10 to the 5th. And that's my final answer, right? So that's how many atoms remain after about 31 days.